Hi students, welcome to my lectures of designing of non-ideal reactors. Okay, before I start the lecture, I request you to follow my lectures from the beginning because every lecture is connected. And a small recap that we are designing of a non-ideal reactor. To design non-ideal reactor means to predict the conversions in this particular non-ideal reactor. And we need three different informations. One is kinetics, second is RTD, third is mixing models. We are into discussion because kinetics is predominantly discussed in the CRE1, and presently we are discussing about the residence time distribution analysis. Okay. So in the residence time distribution analysis, what we have done so far is characterizations. Okay, that means characterization in the sense any reactor have certain properties. Non-ideal, I mean, you can detect non-ideal properties through characterization. One of the few characterization methods are finding the residence time distribution curves using the tracer curve experiments. We are using the pulse tracer inputs. Based on the pulse tracer inputs, we have using some examples of the tracer curve data. We have shown that how to get the information of RTD. That means residence time distribution curve, cumulative time distribution curve, mean residence time, variance, skewness. These are the aspects we have discussed in the using some example. And later on we went into the topic which is called applying this kind of characteristics. That means this residence times, mean residence time, cumulatives, variance, skewness. We have applied this to the ideal reactors first, and we have observed in our previous lectures that how the E of t, F of t curves looks like. What is the mean residence time related to the space time? How is the variance? This is what we have discussed about the ideal reactors. Now we are switching to the non-ideal reactors. Now we have some reference point. Based on this reference point, we can able to judge what the non-ideal reactors are. We are going to start with the non-ideality in the CSTR. Okay, so a small recap that this is what you should keep in mind before we proceed to the analysis of the non-ideal reactors. These are all ideal reactors, which is called ideal plug flow reactor, ideal continuous stir tank reactor, and ideal laminar flow reactor. Mainly we are discussing about the PFR and CSTR, and this is how the residence time distribution curves looks for the case of plug flow reactor and the CSTR. You can see almost all the molecules comes at a specific time, because once you inject the tracer, all molecules comes at a specific time, which is at the time t equal to space time of the reactor. That is what this is, the direct delta function showing that particular phenomenon. Okay, this is F of t, that is cumulative distribution curve looks like at time t equal to tau, all the molecules will come because the fraction of all the molecules come at tau, which is equal to 1. Okay, this is how the CSTR looks like. Then you can see the residence time distribution curve for the CSTR. It's an exponentially decreasing function, which is represented by this equation E of t equal to 1 by tau e power minus t by tau. Okay, here we have already proved that the mean residence time through the tracer curve experiments, which is equal to the space time of the reactor. So the point which touches on the y-axis, it is nothing but 1 by tau. The point here, you can see the blue one, that is it is touched the curve at point which is called 1 by tau. You can see the difference between the CSTR and PFR. Here all the molecules come at one time, because in CSTR, because of this mixing effect, there are molecules which comes at the early time, there are molecules which come at the later time also. That is why it's called exponentially decreasing function. That means there are times because at early time more molecules will come out, at the later time less molecules will come out. This is represented by this exponentially decreasing curve. Here the F of t, you can see the difference between the CSTR and PFR, and you can see the fraction of molecules that comes out of the reactor will slowly increase. It's not like the drastic increase to 1, it's a slow increase to 1 from the early time to the later time. So slow increasing, it will finally at certain point of time it will meet this value of the 1. So we don't need to worry about this particular laminar flow reactor at this instant. So let us take, this is how the ideal CSTR curves looks like, and imagine if this CSTR is behaving non-ideally, then how we can able to identify the non-ideality based on the nature of the curves. Okay, let us proceed. Okay. Imagine, we are discussing about the non-ideal CSTR. Let us, for the reference point, let us take the CSTR. Ideal CSTR has no non-idealities. That means mixing happens at everywhere equally. So the E of t curve will looks in this fashion, exponentially decreasing function, and f of t will slowly will increase. The nature of the E of t function and f of t functions is E of t is equal to 1 by tau into e power minus t by tau. The nature of f of t is nothing but 1 minus e power minus t by tau. This is how the both functions looks like for the ideal CSTR. Now imagine there is a non-ideality existing in the CSTR which is called bypassing. That means there are there are bypassing effects are there. How through the tracer curve experiments people have found out that there are certain molecules which immediately exit the reactor. There are certain molecules which go through the overall volume of the reactor. Because this is called bypassing. Imagine the moment the molecules enter, few fraction of the molecules exit early. You can see the early thing is represented. You can see most of the molecules is exiting because it is away from the stirrer. So there are few molecules which go through the reactor. So in such cases, it is called it is having the non-ideality in the bypassing. Okay, the space time for the ideal CSTR is equal to V by V0. Now how to tackle this? Okay, imagine let us divide, because nu 0 is the volumetric flow rate of the feed entering the reactor. That is why you can schematic representation, you can see that nu 0 is the volumetric flow rate of the feed entering the reactor. Once it enters the reactor, it is divided into two directions. One is bypassing volumetric flow rate and second is volumetric flow rate through the reactor. Okay, this is the situation imagined in such a way that we have divided the volumetric flow rate into two fractions. F is the fraction of this particular flow rate is into the bypass stream, and 1 minus F is the fraction of flow rate that is gone through the entire reactor kind of. So what is the space time of this stream that is entered through the reactor, not in the bypass stream, is nothing but flow, the space time is nothing but overall volume divided by volumetric flow rate which is gone through the entire volume, not in the bypass stream. So space time of this particular reactor containing the bypass stream is nothing but tau into Br, which is total volume of the reactor divided by volumetric flow rate in the main stream, not in the bypass stream. So the total volumetric flow rate is nothing but volumetric flow rate in the bypass stream plus volumetric flow rate through the reactor. So here F is represented. You can see how we have got this values, because during the tracer curve experiments we can able to find out how much amount can be bypassed and how much amount is going through the reactor. So F is the fraction of stream that is bypass, which is nothing but bypass volumetric flow rate divided by total volumetric flow rate, and the and 1 minus F is the fraction that is gone through the reactor, which is volumetric flow rate through the reactor divided by total volumetric flow rate. So F into 1 minus F. And finally, if that is the case, we need to prove that. You can see I have drawn the true curves here. Two curves, one is the blue curve and one is the red curve, and this kind of red curve is indicating ideal CSTR curve, which is starts at the 1 by tau, because we already know that ideal CSTR curve should be starting at 1 by tau. Okay, the one which is starting at 1 by tau is represented here. Okay, then what happens in the non-ideal CSTR? You can see as the majority at the initial time, the moment the tracer molecules or any molecule comes in the reactor, some amount of molecules are bypassed at the t equal to 0 time. You can see at t equal to 0 time, you can see the strip of molecules. You have represented here the blue strip. You can see a strip of molecules entering, exiting the reactor at initial point of time, and only the other fraction enters through the reactor, which is starting at this particular point. The point at which the curve starting is at Vb, nu Br square by V into nu 0. That means ideal CSTR starts at the point 1 by tau on the y-axis, and the CSTR with bypassing, that means non-ideal CSTR, starts the curve at Vbr square by V into nu 0. The top portion is the I can imagine what is this top strip is very simple. There is a set of molecules and you can see this small hump in the curve. This is indicating some amount of molecules jumping out of the reactor because of the bypass stream. So this particular jump I have represented in the strip in this kind of situations. Only thing is, you can see the blue curve is the one gone through the reactor, and the you can see the red one is the ideal CSTR. Okay, ideal CSTR, the curve starts above the bypassing CSTR curve. So if you have done some experiments, tracer curve experiments, if you find out the curve starting below, that means if this is a non-ideal CSTR example, compared to ideal CSTR, the y-axis point starts at below the ideal CSTR. You can see this is what what is the starting point. The starting point of the non-ideal CSTR with bypass stream is nu br square by v into nu 0. The ideal one starts at 1 by tau. Okay, because the one started at high point will, you can see, you can compare these two curves. Okay, the bypass stream is a blue curve and red one is the ideal curve. So which one on the top, which one at the bottom? The one is at the top, which is a blue one. The one is at the bottom is the red curve. Okay, you can see the decay. You can see the red curve will decay faster compared to the blue curve. Why it is decay faster? The one starts at very high will decay faster. The one starts at low point will decay slower, which is an exponential relationship. So the ideal CSTR starts at a higher point than non-ideal CSTR, so it will decay faster. Okay, the non-ideal CSTR starts at the bottom, then it will decay is slower, because the one which is exponential relationship. Okay, this is how, that means by doing the tracer curve experiments and comparing with that of an ideal CSTR curve, you can able to identify whether this reactor, the non-ideal CSTR, is having what kind of non-ideality. If it is having the bypassing, then this kind of curve nature you should expect. Okay, let us move ahead. What is the f of t curve? How you can see the red curve. You can see ideal CSTR. That means you can compare here. Ideal CSTR starts at 0 point and slowly the fraction of molecules are increasing. Whereas in the non-ideal CSTR starts at the higher point. Why it is a higher point? The moment the molecules enter, at time t equal to 0, the majority of the molecules exits, okay, at the 0 time itself. So that is why at 0 time the starting point of the curve will be higher than the ideal curve. You can see this is how the fraction will slowly increase, reach to the value of the 1. So this is what the difference between the ideal curves and non-ideal CSTR, and especially which is having the bypassing issue. So let us move ahead. Let us find out this particular point, how I got the value of this nu br square by v into nu 0 by keeping all this. Before I proceed, you can see what is the space time of this particular bypass reactor. It is a total volume of the reactor divided by volume, volumetric flow rate that is gone through the reactor, not through the bypassing. And for the ideal reactor, what you are supposed to take, space time is equal to volume by total volumetric flow rate. Here you should not take total volumetric flow rate, you should take volumetric flow rate that is gone through the entire reactor. That is why space time of this particular bypass reactor is the total volume of the reactor divided by volume that is gone through the reactor. So this is what the main difference. Okay, and fraction of bypassing is nothing but nu b by nu 0. Fraction of 1 minus f is nothing but mu br by mu 0, which is equal to, okay, don't worry. Okay, now let us find out what is the E of t function for the non-ideal CSTR. Then what is the ideal function for the ideal CSTR? You can see the E of t function ideal CSTR is 1 by tau into e power minus t by tau. Now what is the E of t function for the non-ideal reactor? The function nature remains the same. Then tau, you can see in this equation, is replaced by tau br, and it has to be, the entire equation has to be multiplied with the fraction which is 1 minus f. Okay, then you can compare this equation with the non-ideal E of t function equation. The fraction E of t is nothing but 1 by tau br into e minus t by tau br into 1 minus. F, because 1 minus F is the contribution that is gone through the reactor, that is fraction contributed to the E of t curve in the reactor. So if I replace 1 minus F with this particular equation, then E of t is equal to nu Br by nu 0 into 1 by tau Br into e power minus tau Br. Therefore, this is how we have got the functions. So let us replace what is tau Br. Tau Br nothing but V by nu Br. If you replace this particular function by the V by nu Br, finally you are going to get E of t is nothing but nu Br square by nu 0 into V into e power minus t by tau. You can compare at what is the, see the difference. At time t equal to 0, what is the value of E of t? That means if you put time t equal to 0 in this expression will become equal to 1. So value of E of t at time t equal to 0 is nu Br square nu 0 into V. That is what has been seen here. The value of E of t for a non-ideal CSTR, that means at time t equal to 0, what is the value of E of t? Nu Br square by nu 0 into V. That is how we have got this particular value. Okay, now we understood that this is the function that has to be used for the non-ideal CSTR which is having the severe bypass issue. Okay, now let us find a small problem that assume there is a CSTR which is behaving non-ideally, and it is found from the tracer curve experiments. It is found, okay, through the graphs we can able to find out this particular values and what is the bypass stream, because we know already that from this equation we can able to find what is the volumetric flow rate that is gone into the reactor, and based on this we can able to find out the information how much amount of that is bypassed. So people have done the example, we have done the experiments, and we have found that there is a 30% of the volumetric flow rate which is getting bypassed. So if that is the case, find the space time of the non-ideal reactor. Ideally, what should be the space time? Space time is nothing but, example, the volume of the reactor is given 5 liter, volumetric flow rate gone into the reactor is 1 liter per minute. Okay, if that is the case, what should be the ideal space time of the CSTR? Volume divided by volumetric flow rate, that is 5 divided by 1. Okay, that is equal to 5 minutes. Okay, but it is given that that particular reactor has a bypass of 30%. So the F here, that is F here, you can see that 0.3 which is given as 30%. So what is the actual space time of the reactor is nothing but volume divided by volumetric flow rate that is gone into the reactor. Well, let us find out some steps, that F equal to Vb by nu 0. Nu b is equal to F into nu 0. Given F equal to 0.3, so nu Vb is equal to 0.3 liter per minute. Okay, from this I got the value of mu b. What is total volumetric flow rate? Volumetric flow rate that is bypassing, and volumetric flow rate through the reactor. So volumetric flow rate through the reactor is equal to total volumetric flow rate minus volume that is getting bypassed. That is 1 minus 0.3 which is 0.7 liter per minute. Then let us find out what is the actual space time in the reactor, that is total volume of the reactor by volumetric flow rate that is gone through the reactor. That is 5 by 0.7 which is equal to 7.14 minute. Okay, therefore the tau is equal to volume by volumetric flow rate. It's a kind of the ideal one, it's a kind of non-ideal one. So ideal one is 5 minutes, and because of the bypassing issues the space time of the actual reactor is 7.14 minute. So that is actual space time in the bypassed reactor is greater than the space time of the ideal reactor. If you compare this, and because of the bypassing issue the space time of the reactor has gone increased, okay, compared to the ideal reactor. I hope now you have understood how the CSTR with bypassing kind of analysis. Let us meet with the CSTR with the dead volume in the coming lecture.